Alright, so in this video we're going to solve this problem. So you can actually pause the video and then try this for yourself first. Alright, so first thing we have to do is convert this one into a single battery and single resistor problem, like this. And then second, you have to find the total current from this one. And then you have to find the voltage drop in each resistor. Of course, you can find the current through each resistor first and then figure out the voltage drop in each resistor. But as mentioned in lecture 2, I would like to say that doing this one first and then doing this one is better. Because, like for example, for this case, the resistance value is 3 and 5. So for electrons to pass through 3 ohm is much more easier than passing through 5 ohms. So therefore, it's not really easy and obvious to figure out. Of course, if this was like 1 ohm and 1 ohm, or 3 ohm, 3 ohm, or 5 ohm, 5 ohm, then, and let's say this was like 10 amps going through, then it'll split into 5 and 5. But if it's different 3 ohm and 5 ohms, then it's not very easy to figure out how much current goes through this and how much current goes through that. So it's much easier for you to figure out the voltage drop across this and this because, as I mentioned in the previous lectures, voltage drop for this one and this one will be the same. Okay, so we're going to try this one first. So let's convert first of all this into battery, resistor, and a single resistor. Okay, so we have to combine these two and make that into one resistor. So this is still 6 ohm and 8 ohm. I'm going to combine these two as 1 on 3 plus 1 on 5. And that's equal to 1 over RT. So that's the total equivalent resistor. So this is RT. So we can add them up like this. So you match the denominators, so this is equal to 5 over 15. So multiply this one by 5 and 5. And multiply this one by 3 and 3, then you get 3 over 15. So now these are of the same denominator, so you can add them up. So 8 over 15 right there. So therefore, if you flip this one, so 1 and RT, you just flip that one, and you can also flip this one. So RT is equal to 15 over 8. So this is a little bit less than 2. Okay, a little bit less than 2. And I'm just going to write that down as a 15 over 8 there. Now, because these are all series, we can just add them up linearly. So we can convert this now into a battery and a resistor, just a single resistor. And that resistor's value, so this is, I'm going to call this RT dash because this is different from this one. So RT dash is equal to 8 plus 6 plus this one right here, 15 over 8. So that's equal to 14 plus 15 over 8. And I'm just going to use my calculator quickly. So if you have one, you can pull out as well and verify this yourself. So this is equal to 127 over 8, and which is equal to 15.875. So that's the amount of the total equivalent resistance. Okay, so that's number 1 done. Now we can use this V equals to IR equation to figure out the total current that leaves the battery. And just need to let you know that this one, I'm not sure if I mentioned this before, so this part here, the longer side is positive and the shorter side is negative. But current, there is difference between current, which is also known as conventional current, and electric current, electron current. I would call it electron current. So, you know, all these theories of the Ohm's law, and this is Ohm's law, by the way. This is known as Ohm's law. All these laws were sort of established around 1800s, and back then people thought it was like the positive charges that were moving. but it's actually, electrons that are moving, right? That's why we call them electricity. But back then, everything was established, all the theories and all the conventions were established based on positive charges moving, okay? So when we talk about current, that's also called conventional current, and that's basically a movement of positive charges. We sometimes call them positrons, okay? But you can just think of them as positive charges, positive like electrons. So electrons are negatively charged, okay? So we can figure out so when we use this equation, it's always the conventional current. So we're going to use this one to figure out the current. So the voltage is equal to IR, and therefore I equals to V over R, and V is equal to 12 volts. And let's divide that by this one here, which is 15.875. That's the resistance value. So 12 divided by the answer. I'm just going to do it in my calculator. So the total current is equal to about 0.756 if I round it up to the third decimal place, and that's amps. Now, so that's done. Total current is done. So using the total current, we can figure out the total of the voltage drop across each resistor. So this much current is passing through 8 ohms. So again, using this equation here, what's the amount of voltage that's used in here? So that's equal to I, which is this one, times by the 8, which is the R. So if I do that, then that's equal to 6.0. I'm going to round it up to the third decimal place. So 0.047, and that's volts. And what's the amount of current that goes through this? That's equal to 0.756. Okay, and that's amps. And of course, the same amount of current the same current actually splits into those two, but we don't really know how much this one divides, how this one divides into those two, as I mentioned before. But we know that this one will recombine here at this junction here, and then will pass through the 6 ohm as the same value. So we multiply the same current, which is the total current. So total current passes through 6 ohm as well. So this one times by 6 there. We're going to try that. That's equal to 4.535 volts. And of course, 0.756 amps pass through it. So that's for that resistor. These three are for that resistor there. Now, because these are in series, we can just subtract these voltage values from this 12 volts. So if I do that, 12 minus 12 minus this one here, 4.535, and the minus 6.047. That means I have 1.418 volts left for these two. And as I mentioned before, this one doesn't divide into two and apply, it doesn't go like this, 0.7 and 0.7, so that they add up to 1.418. But rather, this remaining voltage applies equally to this one and this one. So this one is 1.418 volts, and this is also 1.418 volts. So for these two, which were in series, we used the total current and multiply that by the resistance value and figured out the voltage, right? And we figured out this voltage here using the current. But in this case, we don't have to use the current to figure out the voltage, because this is like the that's like the remainder. You can just apply that equally right here, here, and here. And from there, you can divide this one by this one. You see, voltage divided by resistance is current. So I'm going to divide this by this and see what I get. So 1.418 divided by 3, that gives me 0.473, and that's the amount of the current. And I'm going to divide this one by this, so 1.418 divided by 5, and this gives me 0.284 amps. Okay. And let's actually check this one. I'm going to add these two. So this is the current that goes through this part of the circuit, and this is the current that goes through this part of the circuit. But if I combine these two, I must get this total current there. So I'm going to add that with 0.284 plus 0.473, and what I get is 0.757 amps. And that's very close to this value here, isn't it? The error of 0.001 amp, I think that comes from the rounding error. Okay, so that's insignificant really. So that's the answer. And so you can see that for each bulb or resistor, we have three values. How much what the voltage drop is across that resistor, it means this here means 6.047 volts has been used by this resistor here. This one has 8 ohms of resistance, and the total current that passes through that resistor is 0.756. So it's a good practice to have all these three quantities specified for each resistance or each bulb. All right.